All right, so we're going to be moving on and looking at further application of Newton's universal law of gravitation. This is part 2 of applying this, and it's on page 35 of your unit handout. So we're just going to continue to apply Newton's universal law of gravitation. And we'll plow right into an example here. During a lunar eclipse, the moon, earth, and sun are aligned pretty much in a straight line as shown in the diagram. This diagram is not to scale. Okay? If that were actually what was going on in our little corner of the solar system, we would be burnt to a crisp a long time ago. Clearly, not only are the sizes of these wrong, but the distances are wrong. Just for kicks, I would like everybody to take on your calculator this distance, which is the distance between us and the sun, and divide by this distance, which is the distance between us and the moon. And I want to say it's going to be somewhere around 400 or 500. I don't know exactly, but somebody let me know what you get when you divide those two numbers, 391. So let's just round it to 400. If I were to draw this to scale, the moon would have to be like right there. And again, we have a problem in this diagram with the size of the objects. The radius of the Earth compared to the radius of the sun is very, very tiny. So this is a diagram from your textbook. It's just what they use. What we want to do, and the question says using the data in the chart below, it should really just say find the net gravitational force because we already have the information there. What's the net gravitational force acting on the moon? And I want to highlight for you, everybody, that we are finding a gravitational force, but it is the net gravitational force. It is a net force acting on the moon due to the sun and earth. Now, the moon is attracted to the earth, and I'm going to draw in that force of gravity on the moon. The moon is attracted towards the earth, and the moon is attracted towards the sun. I don't know which is bigger. Well, I do, but we don't know as a class which is bigger yet unless we do the calculations, and we're going to in a minute. But I want to talk briefly about something here because some people will look at this and say, I'm going to label these forces. Actually, I'm going to do it here where I got a bit more room. We have a force due to gravity on the moon due to the earth, and we have a force due to gravity on the moon due to the sun. And again, I don't know how long I should draw those, but let me label them. This is the force due to gravity between the moon and the earth, and this is the force due to gravity between the moon and the sun. Some people look at this and say, well, how can the moon be attracted to the sun when the earth is between it? And I get that concern or that question. But if you stop and think about it, when you're standing on the surface of the earth, there is a force of gravity on you. I don't know what I'm drawing here. There is a force of gravity on you that is your weight. Now, if you decide that instead of standing there, you're going to stand on a wooden platform, you don't block out the Earth's gravitational pull. Gravity extends through space, and it also extends through mass. So there is a gravitational force of attraction between the moon and the Earth, and also a gravitational force of attraction between the moon and the sun. We are focusing on the forces on the moon because the question says, what is the net gravitational force exerted on the moon? Okay, so that's why we're looking at the forces on the moon. Are there forces on the Earth and the sun as well? Yes. The Earth is attracted to the moon. The Earth is attracted to the sun. The sun is attracted to the Earth. The sun is attracted to the moon. Everything is attracted, but we do this problem by focusing on the object of interest. So what we have to do is use Newton's universal law of gravitation to calculate, and now I'm going to be a little clearer on my abbreviations, the force of gravity on the moon due to the Earth, and we have to calculate the force of gravity on the moon. I don't mean the force of gravity when you're standing on the moon. I mean the force of gravity that the moon experiences. Now, due to the sun. And I'm not going to show my work here, everybody. We're going to do this using Newton's universal law of gravitation, which is G m1 m2 over r squared. So listen very carefully, and then I will let you loose on your calculator to get the numbers. To calculate the magnitude of the force of gravity on the moon due to the Earth, to find this force, you're going to take capital G times the mass of the moon times the mass of the Earth divided by the distance between the moon and the Earth squared. So for the first one, you are going to have to take, what color haven't I used? To calculate this one, you are going to have to take the G times the mass of the moon times the mass of the Earth divided by this distance squared. To calculate the force of gravity on the moon due to the sun, you're going to have to take G times the mass of the moon times the mass of the sun divided by the distance between them squared. So you're going to have to add those two distances together in your second calculation. So I'm going to give everybody a few minutes here to calculate those. As soon as you get an answer for the force of gravity between the moon and the Earth, please type it into Google Chat and type moon Earth and then the number. And as soon as you get an answer for the force of gravity between the moon and the sun, do the same thing. Cole, I'm just curious if you had a chance to find out what happened with that question. Oh man, that's frustrating. That happens a lot. It happens a lot in calculus. If you end up taking calculus with me, sometimes we spend 15 minutes trying to find out what we did wrong, and it's just, we forgot to put a squared on an x, or we switched two numbers. I'm glad you found it. The important thing, Cole, is you understand how to do the work. And by the way, with this question, the things that I'm asking you to calculate here are, yeah, I know, Cole. The things that I'm asking you to calculate here are not our final answer. So I don't know how this plays into it, but you don't want to round anything for these two calculations. Keep working at it. I'm going to go out on a limb and say, since we've got 3 people getting 1.98 times 10 to the 20 newtons, which is I mean, think of the size of that number. That's huge. That is 200 million newtons. So I'm going to do it now, 6.67 multiplied by 10 to the negative 11, multiplied by the mass of the moon, which is 7.35. I'm always amazed that we know these numbers. We know the mass of the moon. That's boggling to me. Multiplied by the mass of the Earth, divided by the distance between them, which is 3.84, multiplied by 10 to the 8 squared. Always double check, especially when you have lots of numbers that you're working with, always double check all of your entries. G is right, the mass of the moon is right, the mass of the Earth is right, and the distance between them is right. So what I get is the same thing that everybody else got, 1.98. 1.98 times 10 to the 20 newtons. Like I said, huge, huge force. And now I'm starting to get an answer for the force of gravity between the mass and the sun. I'm not going to do the calculation just yet. I want a few more people to do it. Remember with this formula that you are going to have to use the total distance. So for the green calculation, what you're going to need to do is add these two numbers together. You will need to add this plus this in order to get R. Andrea, looking at your answer, I think you did that, but I think maybe you forgot to square R. Now Liam's done already. We're going to have to add, oh, you forgot to add the G. Oh yeah. And that's interesting. As I highlighted everything, I thought I'm not mentioning G. So when you do that, I'll just do the calculation. And again, I would recommend doing this all in one shot. You're going to take capital G, which is 6.67, times 10 to the negative 11. We have to multiply by the mass of the moon. We have to multiply by the mass of the sun. And then we have to divide by that distance, which I'm just going to put in brackets. I could add those two numbers together on my own on the side and then put it in, but you know what? I really don't care what the sum of those two numbers is. I don't need to find out what it is and then square it. I can just put it in this way. 3.84 times 10 to the 8 plus 1.5 times 10 to the 11, close brackets squared. Again, an awful lot in there. 6.67 times 10 to the negative 11 times 7.35 times 10 to the 22 times 1.99 times 10 to the 30 divided by that squared. By the way, it looks okay. So what we get is, for that, you get 4.31 times 10 to the 20. But I want to, science and physics is about precision. If you look over on the left-hand side here, I do not have absolute value signs. So to say the force of gravity between the moon and the Earth is 1.98 times 10 to the 20 newtons, we want the direction of the force of gravity on the moon, and in our diagram, it is to the right. Towards the Earth. And in our diagram, the force of gravity acting on the moon due to the sun is to the right. And by the way, I guess I can maybe do a better job of scaling things now. Even though, look at this is interesting. Even though the sun is so much further away, even though the sun is so much further away, the force of gravity acting on the moon due to the sun is over twice as large. Now, Liam got an answer of 6.3 times 10 to the 20. I'm assuming you got that by adding those two numbers together. And the reason why Liam added them together is those two forces are in the same direction. We're back at the basic idea of how do you add forces. And to add two forces that are in the same direction, thank you, Liam, you're simply going to add the numbers together. So 1.98 times 10 to the 20 newtons to the right plus 4.31 times 10 to the 20 newtons to the right is found by adding those two numbers together and getting 6.30 times 10 to the 20 newtons to the right. Can I get somebody else to confirm that that's what you get when you do add the numbers together? Okay, not a problem there. So before we go on and take a look at another question, does anybody have any questions with this one? All right, let's take a look at the next question. It says, determine the net gravitational force on mass B due to the other masses. Now, these masses are not planetary masses. They're not huge. So we're not going to get large forces. We're going to get very, very tiny forces. The reason why we have to learn how to do these types of problems is in Physics 30, we do a lot of work with charges. And when we analyze motion of charges, we have to do it with net forces. So we're going to do the same thing as we're doing here in Physics 30, but with electric forces. Let's see here. The net gravitational force. Let's highlight a couple of words for you. Net, that means total, on mass B. So if we want to find the total gravitational force on mass B, then we need to find all of the gravitational forces on mass B and add those forces together. Now, looking at the diagram, there will be a force of attraction between B and A. So there will be a gravitational force on B towards A. This is the gravitational force on B due to A. Now, there's another gravitational force acting on B, and it's due to an attraction between B and C. So this other force that I'm drawing would be the force of gravity. But this force of gravity is on B due to C. I have a question for you without doing any calculations, everybody. Is it possible to reason out which of those two forces will be greater? So which do you think is greater? Do you think the force on the left, we'll just go left and right, BC is greater? I think everybody is basing, oh, and then Ben says the left is greater. I think most of you are basing it on the fact that the mass of C is more. But now Ben's pointing out the distance between A and B is less. And by the way, The distance being less is normally a bigger factor because of the inverse square law. But the distance isn't that much less. I mean, we're going to have to actually do the calculations. And that's your job right now. You need to calculate this force using, well, what are we going to use? We're going to use the force of gravity equals G m1 m2 over r squared. So for the force on the left, you are going to have to take, for this force, you are going to have to take G times that mass over this distance squared. For the force on the right, you are going to have to take G times this mass over this distance squared. We're not going to be adding the distances together because we're measuring the distance from B to A and from B to C. So they're already given to you. When you get some answers, put them into Google Chat, but put them in so that I understand which one you're finding. You can say left, you can say right, you can say AB, you can say BC. By the way, I'm pretty sure that the force to the right will be greater. Looking at the masses, I can see that, well, I don't know. I'm pretty sure. I'm getting a couple people chiming in here that they're getting 3.37, 3.38 times 10 to the negative 7. A few more people agreeing. Now we're getting a response for the force to the right. And Andrea agrees with that. Liam and Andrea are getting 6.05 times 10 to the negative 7 to the right. Farhan got 3.4 times 10 to the negative 7 to the left. I hope, Farhan, that you got 3.37. Like there's more digits there. I don't want to leave anybody out in the cold here or in the dirt, but I'll give you just maybe one more minute to finish your calculations. I'll start doing my calculations up here, and some of you, I'm sure, are almost at the final answer now, if not at the final answer. So between A and B, I have 6.67 times 10 to the negative 11. We are multiplying by the mass of A, which is 380 kilograms. We are multiplying by the mass of B, which is 270 kilograms. And we are dividing by 4.5 meters, always remembering to square it. Double check my entries. They look okay. So this is what we're getting for that force. And then for the next one, whoops, that's not what I want. 6.37 multiplied by 10 to the negative 11, multiplied this time by 270, and multiplied by a whopping 840. This 840 is what tips the scales towards the right. That 840 kilograms is, I think it's a little bit more than 3 times, maybe not. No, it's a little bit more than twice the mass of A. And then divide by 5 squared. Double check my numbers, look okay. So this is the force I get here. So what you are getting is, this is being a little lazy, but this is newtons. And it is acting on B to the left. This is newtons acting on B to the right. So net means total. You have to add these two forces. I don't mean you add the numbers together. I mean you add the forces. And now we go back to, like, I think it might have been day 2 or 3 in this course. Even though we hadn't really studied a lot of vectors, we were introduced to the concept that displacement was a vector, and to add vectors that are in opposite directions, you subtract the numbers. This goes back to Andrea's point the other day about subtracting the smaller from the bigger. So since we have a larger force to the right, and if I were to draw this now maybe more to scale, it might look something like that. Larger force to the right, I'm going to subtract those two numbers. So I'm going to take this one and subtract 3.3794 times 10 to the negative 7, and we get 2.67 times 10 to the negative 7 newtons to the right. And that's the net force. That's our answer. The reason it's to the right is there was a greater force to the right. That's just, you know, the fact that we're subtracting the magnitudes and putting right on for the direction, that's just basic vector addition, adding vectors in opposite directions. Any questions with the second example? All right. So what did we do in example 1? We wanted a net force on the moon. We found all the forces on the moon, and we added the forces together. The two forces that we added in example 1 happened to be in the same direction. So when we found the total, we just added the numbers together. In example 2, we were asked to find the total or net force on mass B. So we found all of the forces on mass B, and we added the forces together, but they were in opposite directions. So when you add forces in opposite directions, you subtract the magnitudes. Well, now let's look at the third situation. We are asked to determine the magnitude and direction of the net gravitational force on the 45 kilogram mass in this arrangement. And by the way, I didn't do this, I probably should have. These distances form a 90-degree angle in here. If they didn't, you wouldn't be able to solve the problem without knowing the relative directions of those. I'm not going to muddy up the diagram by putting that in there. What I'm going to do instead is draw on here forces we're interested in. What did I say, Liam? Did I not say triangle? I'm just curious. Oh, okay. So what we're going to do here is find the net. What we're going to do here is find the net force on the 45 kilogram mass. So again, you know, at the sake of being overly repetitive, net means total. We have to find the total gravitational force, and it is on mass on the 45 kilogram mass. So what are the forces on that mass? If we want to find the total force on that mass, we have to find all of the forces on that mass. And there will be a force of gravitational attraction on the 45 kilogram mass because it's attracted to the 35 kilogram mass. You know, is there a force on the 35 kilogram mass towards the 45? Yes. But we don't care about what's happening to the 35. We care about what's happening to the 45. At the same time, there is a gravitational force of attraction between the 45 kilogram mass and the 75 kilogram mass. When we start to compare the sizes of these forces, this gets tricky. Because the 75 kilogram mass is twice as massive as the 35 kilogram mass, that would already say that the gravitational force with the 75 kilogram mass is twice as great. But since the distance is about half as great to the 35, that would mean the force between the 35 and the 45 is actually 4 times greater. So my prediction is that this force will actually be around twice as great as this force. But let's calculate them. That's what you need to calculate. So I'm going to give everybody a minute. You want the force of gravity on the 45 kilogram mass by the 35 kilogram mass. And you want the force of gravity on the 45 kilogram mass by the 75 kilogram mass. These GMM over R squared calculations should be very simple right now. You have to make sure that you enter numbers in correctly, but the actual physics and the task at hand is not difficult. So give you a minute or two to do that, and then you can start typing your answers. You know, label your answers, say 35, and then that way I know you're talking about the horizontal force. Now, be careful here. You got to make sure when you divide by that distance of 26 centimeters that you use standard units of meters. The reason for that is capital G has units that have Newton meters squared per kilogram squared. And one of you, Mackenzie or Liam, didn't do that. And this is the first time we've encountered this, so I should have mentioned this earlier. I want to make sure that you get my drift here. This distance must be divided by 100 and written or expressed as meters. And that's probably the case, Andrea. I'm going to finish my calculation here. 6.67 times 10 to the negative 11 multiplied by 35 multiplied by 45 divided by 0.26 squared gives me 1.55. Is that the number you guys were getting? 1.55 times 10 to the negative 6 newtons. And you both get that now, Andrea and Mackenzie, that's good. When we do it for the other one, I'm going to store this as A. Doesn't matter what I store it as. I just want to be able to pull it up again later. When I do it for the other pair of masses, multiplied by 45 multiplied by 75 divided by 0.42 squared I get this number. So the force between the 45 and the 35 kilogram mass is 1.55 times 10 to the negative 6 newtons left, looking at the diagram. The force between, or the force on the 45 kilogram mass due to the 75 is 1.27. Wow, I was a little bit off on my estimation. Times 10 to the negative 6 newtons down. I thought the one to the left would be a lot bigger than the one down. So it's a tricky thing to try to figure out in your head. Looks something like that. So now you have to add those forces. Okay. These two forces are not in the same direction, so it's not as simple as adding them, adding the numbers. They are not in opposite directions, so it's not as simple as just subtracting them. However, they are at right angles. So, interesting. Oh, my computer just ran out of memory, I guess. What we have to do is add them, and although on your diagram you have these two arrows, you have to now redraw this. And I don't want you to draw it on your diagram. You draw it someplace else. We draw these tip to tail. Again, I hope you remember that I like to draw the horizontal first. And this is 1.55 times 10 to the negative 6. This is 1.27 times 10 to the negative 6. Before I go on, I just want to make sure. Well, 1.276. So now you have to find this. There's very little in this course, everybody, that is not cumulative. I go under the assumption right now that everybody knows how to find the total of those two vectors by using the Pythagorean theorem to determine the hypotenuse and to find the angle you use tangent. So tangent of the angle is opposite. These are all in newtons, divided by adjacent. And then you can go inverse tan to get your answer. I'm not even going to write down the Pythagorean theorem here. You're going to square both of those numbers and add them together. Can we confirm here that the magnitude of the net gravitational force is equal to 2.01 times 10 to the negative 6 newtons? Can I get a couple other people to confirm that that's what you get? Okay. And can I get anybody else to confirm that that angle ends up being 51 degrees? No? Let's double check. Liam's saying he wants to do a recalculation here. 39. Okay, I want to stop here. I just want to make sure because I may have made a mistake. Did I write those two numbers in the places they should be? Is it 1.55 times 10 to the negative 6 to the left? I did. Okay, so it's actually 39 degrees then. And I don't know what you want to say here. I guess we could say if this were a map, then we would say south of west. I like the idea of just saying 39 degrees equals theta, because theta is given in the diagram. You could say 39 degrees down of left if you wanted to. So what you're doing here, everybody, in this lesson is you are taking what you learned yesterday, which was new, and you are taking what you already knew about vectors and the fact that forces are vectors, and you're taking what you've been taught about net force means total force, and you're rolling it all into one physical ball of stuff. Okay? I want to just briefly here, I want to help you as much as I can. And sometimes, this happened earlier and it's happened in the past too, sometimes there's a problem, I think, with checking your calculator work. And it happens when you use a TI-84. So when I take a calculation like 6.67 multiplied by 10 to the negative 11, and then multiplied by 650, multiplied by 5.97 times 10 to the 24, divided by 4.15 times 10 to the 6 plus 6.37 times 10 to the 6, quantity squared. I don't know if you remember, but I'm pretty sure those were the numbers for the satellite question we went over. G times the mass of the satellite times the mass of the Earth divided by the distance from the center of the Earth to the satellite. When I enter that on a TI-84, and you guys with a TI-84 know this, something happens partway through my typing. Times 650 times 5.97, and it's already started to happen. I think most people, when you type stuff in your calculator, are looking at the keys and not at the screen. And what happens here now is I can't look up on the TI-84 and see what I've entered. I can scroll around, but I think it's easier, let's just finish this, divided by bracket 4.15 times 10 to the 6 plus 6.37 times 10 to the 6 and bracket squared. That's not what I meant to do. I'll do it back here further. So you type this all in, and this is where you're at on the TI-84, and you hit enter, and you hit enter here, and you're getting the wrong answer. Now, I know I did that, Cole, but I'm doing this for a reason. There's something here that I forgot or that I made a mistake in, and I think the one that I changed it to was I changed it to 50 instead of 650. So I can't look up and see what I've entered. Whereas in this situation, I can look up and see what I've entered. So if I entered only 50 instead of 650, I could see it. I'm just pointing out that with the TI-84, there's a disadvantage to that thing. Now, if you want to, it changes the layout of things, but I recommend it. You're going to have to decide. If you go to mode on your TI-84 and scroll down, there are two versions of the user interface, Math Print or Classic. And if you go to Classic and you start typing stuff, it appears the same way as it appears on a TI-83. The disadvantage is when you square something, no, it still looks pretty good. When you raise something to an exponent now, it just puts that hat rather than shifting things up. But you can always switch back. Thanks, Farhan. So that's it for the day. I have to take off here in about 10 minutes here for my appointment. My smartboard just crapped out, made it to the end of the lesson. That's awfully big. You can see what the assignment is. There are, I believe, 2 or 3 problems to do. I think if you do the problems in the handout, that's good enough.